Good evening. My name is Walter Hammond. I am the Vice Chairman of the AIAA Central Florida Section, and we are privileged tonight to have as a guest speaker a distinguished lecturer from the AIAA, the Institute of Aerospace and Aeronautics, who is going to talk about missile design, development, and systems engineering. Uh, Gene Fleeman is an authority in the field. As you can see on the screen, he's got a book out called Missile Design and Systems Engineering. I have a copy right here with me, and it is available from the AIAA bookstore. You log on to aiaa.org and can order this book. This book is a tome that he's going to basically give us an introduction to the field tonight. But this is an 850 some odd page book. No, it's almost 870 pages, count the appendix. And one of the things I want to tell you is that if you buy this great book, which I think is well worth the little money that it costs, there's some supporting materials at the back, and it gives you a password, and you can log on there and get all kinds of materials. He's got videos, he's got presentations, he's got all kinds of additional resources. So again, I recommend everyone listening to this to consider buying this book, Missile Design and Systems Engineering by Eugene L. Fleeman, and you won't regret it. I have certainly cherished this book and use it often in my work in the aerospace industry.
Thank you.
The Central Florida section is comprised of the counties shown on the screen there. We are in Central Florida, but we are very large. We have, I think, something around 600 members spread out in the Central Florida region as shown here. And we basically, we're making this presentation. I am in Orange County, but our section has a number of activities that are very worthwhile for you to attend. We have been posting things on YouTube recently, and we are going to begin a series, like a monthly series on presentations of topics of interest by selected individuals. We also have two student branches, one at the University of Central Florida and one at the University of Florida. And we go all the way out to Tampa, so as you can tell on the screen there. And then I want to say that we're having an Ascend forum. The AIAA is hosting a virtual forum called Ascend. It'll be held in November 16th to 18th. I'm chairing a session on model-based systems engineering, but if you want to attend that forum, it doesn't cost very much. It's a virtual forum, and you would find it worthwhile. There's going to be a ton of good presentations on the broad sphere of systems engineering and aerospace systems in general. I'm going to turn it over to Chris, and he's our chairman, Chris Stevens. He's going to tell us a little bit about the SECME glider competition. And Chris?
Yeah, thanks, Walter. Yeah, I'm Chris Stevens. I'm the chair of the Central Florida section of AIAA. We're working with the University of Central Florida to host the SECME Regional Glider Competition next spring. So it's a competition that's actually taking place now with elementary, middle, and high school students. We sent out a video instructing the teachers and parents of all the rules for the competition and giving them some advice and some guidance on the airplanes and how to teach all the students. So they're off building their gliders now. They're going to be pretty big. They're minimum 2-foot wingspan, so they're going to be pretty big gliders carrying a bunch of marbles. It's going to be a lot of fun, and we're going to hopefully get together at UCF in the spring on February 13th, and we will be looking for some volunteer judges for that. So any college students, professionals, educators, anyone interested in the Central Florida area that's looking to volunteer, we'll send out some more information probably in January. We may also do our backup plan of going to a virtual competition, so if that happens, we might need virtual judges that can watch the videos and help us judge online. So looks like that's going to be a lot of fun. Like Walter said, we have a lot of great opportunities coming up. Those workshops we're working on are the monthly events, as well as some great events for the spring. So keep an eye out on our Engage and social media for all the great stuff we have coming up.
Okay, and I also want to add that there is a SciTech forum in January in Orlando that will be virtual as well. That is the big, one of the largest forums that the AIAA hosts every year annually in January of every year. It will be virtual. Go to AIAA.org to get more information on the SciTech Forum 2021. We have some scholarship applications open now. Chris, do you want to talk about these a little bit?
Yeah, so for college students studying anything aerospace related, so aerospace, mechanical engineering, things like that, anybody that wants to go into the aerospace industry that is a student at either UF or UCF, so they have to be at a student branch in our section, we are offering a $500 scholarship. So our application is available on our Engage page, or you can contact us at aiaa.central.fl@gmail.com to get information, and we can send you that application. So it's going to be due at the end of this year, and you do have to have been a student AIAA member for greater than 1 year in order to get that scholarship. But it's a great opportunity for the students that are studying hard here to take a little bit of pressure off, pay for some books or something, and help you guys get ready to join the aerospace community.
Yes. So, and again, our section is going, we often partner with the Cape Canaveral section. They're having a networking event coming up in November. I think it's I forget the date, but anyway, I can provide, we often liaison with them and provide information. Let's give you that date. So their presentation is going to be November the 19th. That finishes the intro. I would like to introduce our speaker. So Gene Fleeman is an expert in, and I can tell you he's an expert in missile systems design and engineering. He has over 50 years, over 5 decades of experience in the field of missile design and engineering. He formerly managed missile programs at the Air Force Research Laboratory, headquartered at Dayton, Ohio, at Wright-Patterson Air Force Base. He was in what was then the Flight Dynamics Laboratory. He also worked at Edwards Air Force Base, at other parts of Air Force Research Laboratory that have to do with missile design. He's been at China Lake, which is the Navy counterpart to the Air Force's Research Lab for Missile Design and Test. And he also worked at Rockwell International, at Boeing, and at Georgia Tech. He worked on the Hellfire missile and a number of other missile designs while at Rockwell, and he basically is an authority in the field. He's the author of 200+ publications and 3 textbooks. This is the latest textbook. He's also working on a 4th textbook that is right now being processed by the AIAA, having to do with missile design. Tonight, he's going to talk about missile design, development, and systems engineering. He's going to emphasize, his talk is going to emphasize physics-based prediction methods for enhanced speed, accuracy, and for the conceptual design process. He also teaches a short course that has been held over 100 times in 15 countries and 5 continents. And additional information will be available on his slides that he is going to be presenting this evening. So Gene, I would like to introduce you, and I'm going to stop my screen share, and now you can take over and begin your talk.
Thank you. Thank you, Walter. Thank you, Chris. Okay, so let's bring up my presentation, and I'll go to slideshow, hopefully. And I think you all can see this okay, I hope? Yes? Great. All right, we'll get started. Let me see, I guess, let's see, there's a way of showing participants on the side. I'll move that over out of the way a little bit. And
I believe we have chat enabled as well, right?
There's a chat also. Yes, I'll add that in, but put it out of the way a little bit. So we're able to get started here. Okay.
Okay, and I'm recording the presentation as well.
Thank you very much. All right, well, this will take about 60 minutes. We did a dry run yesterday, and I also went through and I've done this presentation, as Walt mentioned, a number of times, and so it'll be about a 60-minute presentation, including videos. So it's an overview. As Walt mentioned, I've got hundreds of slides I do in a long short course, or either on site or in as far as or on the internet. But it was a challenge boiling this down. But I think I try to give you hopefully an overview that has a pretty good breadth to it and enough depth that it's hopefully be able to sort of make sense what I'm talking about. But that is part of my challenge. But I will dealing, as you said from the title, the design aspects of the missile, especially from conceptual design point of view. I find it's important to get that done right. If you don't do that right at the beginning, and you get downstream on that program, you start spending a lot of money in hardware and testing and whatever, and you got to go back and redo things. You don't want to. You want to make your mistakes on paper early. So I have physics-based type things. I'll be giving illustrations of, and then the development aspects of how one develops the subsystems leading to the missile system, and also system engineering, including integration with your launch platform and also the fire control system. So these are sort of notionally showing it as you go from each of those steps, and I'll be illustrating that in this presentation. Okay. If you look at a missile is a system. It flies through the air. It can even be autonomous. You got to tell it where to go, obviously. But here I have an analogy of the English boxing champion in the 19th century. And the missile is kind of like a human in a way. If you look at a seeker on the missile, looking at the target, it's like the eyes of the human looking at a target. If I look at the electronics on the missile, it's like the brain of a human telling what the missile wants to do. If the missile is wants to knock out a target, like the boxer wants to knock a target out, well, the missile warhead is like the fist of the boxer, putting energy on the target. And then you got to direct that missile toward the target. And the flight control of the missile, depending on what kind you have, we'll talk some more about that, canard control or tail control or whatever, is like the arms of the boxer that impacts the target. And then the structure of the missile holds the missile together like the ribs of the boxer, the bones of the boxer. Missile has to go toward the target with a rocket motor or an engine of some sort, turbojet or ramjet or whatever. And just like the legs of the boxer lets the boxer move toward the target. And then a missile needs stabilizers, usually, especially air-to-main controlled missiles, so that they both don't tumble as they fly through the air. Just like a free flight projectile or like an arrow. If you're shooting an arrow out of a bow and arrow, you put tail feathers on the arrow for stability, just like the feet of the boxer provide stability. So there is an analogy, and that's why all these subsystems have to work together to do the job, to knock out the target. Just we got a little technical problem.
No technical issue, folks. We're fixing it.
Are we back online? Great. All right. So let me keep moving here. A point I was making about these measures of merit, and there's so many of them, and you'd like to make them as good as you can, but typically if you take a measure of merit and take it to an extreme, you're going to aggravate another measure of merit. So one reason Walt mentioned, I've done this for decades, 5 decades, is to me it's as much of an art as a science. It's very interesting because beauty is in the eye of the beholder, and you want to have a balance in your measures of merit. And so these are, without spending too much time, lightweight, good flight performance, be robust against countermeasures or different kinds of uncertainties, have a nice warhead, be accurate, be compatible and not messing up the observables of your launch platform. If you're on, say, an F-22 or an F-35 or something of that sort, try to be survivable if you're a cruise missile. Try to be safe if the missile won't blow up, mess up the launch platform, kill people. Be reliable, be low cost, especially tactical missiles, and have good integration. So that's the challenge of doing a balanced design. Okay, so I'll talk about some of those. I know many of you down there are missile defense oriented. And so as an example of system of systems, here an example of intercontinental ballistic missiles, let's say. The United States has a system, the ground-based missile defense system, where we have an exo-atmospheric kill vehicle. And then for shorter range missiles, intermediate range, medium range, very short range, that we have exo-atmospheric, endo-atmospheric, and typically overlapping capabilities. And so you got to work the system of systems of not just the missile itself, but you need a good command control, battle management, communication. You have a good launch platform integration. You have good fire control, good threat warning through satellites or unmanned air vehicles or whatever. So that's the challenge. So I have a video here I'm going to show you now on missile defense.
Advanced ballistic missile threats are potentially the most dangerous menaces we will face as a nation over the next decade. The mission of the Missile Defense Agency is to develop and field an integrated, layered, increasingly robust ballistic missile defense system to defend the United States, its deployed forces, allies, and partners against all ranges of enemy ballistic missiles in all phases of flight. Today, 30 operational ground-based interceptors deployed in missile fields at Fort Greely, Alaska, and Vandenberg Air Force Base in California protect the U.S. homeland against ICBMs launched from today's regional threats. The Homeland Missile Defense Architecture also includes early warning radars in Alaska, California, Thule, Greenland, and Filingdales in the United Kingdom. Upgraded early warning radars at Clear, Alaska, and Cape Cod, Massachusetts are planned for later in this decade. The system also receives threat detection and tracking cues from ANTPY-2 X-band radars in 4 base modes, such as the one currently deployed at Shiriki, Japan, and Aegis BMD ships in the long-range surveillance and tracking mode. The ANTPY-2 is a high-resolution radar capable of tracking all classes of ballistic missiles and identifying small objects at long distances. For regional missile defenses, the Missile Defense Agency has developed and fielded a range of land and sea-based terminal and mid-course capabilities to counter short and medium-range ballistic missiles. The Patriot Advanced Capability 3 conducts short-range ballistic missile defense. This interceptor is highly transportable and is deployed today in multiple regions, from the Pacific region to Europe to the Middle East. A terminal high-altitude area defense, or THAAD, is also a transportable missile defense capability. Each battery has interceptors, a launcher, an ANTPY-2 radar and terminal node, and fire control and communications, and can destroy targets inside and outside the atmosphere. Aegis BMD ships using the Spy-1 radar, network sensors such as the ANTPY-2, and the Standard Missile-3 Block 1A guided missile offer a flexible regional missile defense capability against short and medium-range threats. A command, control, battle management, and communication network, supplemented by regional command and control nodes, manages the full system.
So you can see it's a real complex activity to do a missile system design and development. Talk about system engineering, and these are some of the aspects that one would consider. Part is your modeling and your analysis capability, and I'll talk some more about that later. And then integration with your launch platform, whether it's an aircraft or a ship or a combat vehicle, and its fire control system also, that's part of it. And then requirements flow down, where you take a given high-level requirement, like say probably a kill, and you do an allocation between the warhead lethal zone radius and the accuracy of the guidance, flowing that down a little farther than the guidance area, break out the components all the way down to even, some little part of a subsystem is part of that requirements flow down. So that's part of the system requirements. And then finally, flight simulation. We do a lot of that. We do a much better job now than we did, say, 50 years ago. And so 50 years ago, we did a lot more flight testing. I kind of miss those days because simulation is great, but they call garbage in, garbage out at machine speed, gigawatts, is that you have to make sure you've got good input data and you get a good model in the simulation. So that's good for verification, but the ultimate is validation. So you still need some flight testing, but we don't have as much now as we used to have. Anyway, I'll talk about those aspects. So what's happened now, as I said, over the last 50 years, is this long acronym: Command, Control, Communication, Computers, C4, Intelligence, Surveillance, and Reconnaissance. It's been revolutionary because of the electronics and the sensors we have today, is that we can do near-time targeting and high accuracy, and that we could not have done, during the Cold War. And so these off-board sensors we have, satellites are available. They're tactical satellites. Also, unmanned air vehicles are like a 4-man satellite. you can take that information and you can go after certain kinds of targets, like say time critical targets, which are often the most difficult to handle. And these are some examples of those. And you can go with various launch platforms shown here. So that's one of the things that's happened in recent years is the ability to do that. I've got a video here by the Hermes unmanned air vehicle, which will give an example of targeting.
A 2.5-meter long internal payload bay and external wing hardpoints enable easier customization to a wide variety of missions using various multispectral payload configurations. With standing configuration, the Hermes 900 wide area optical and SIGINT payloads enable effective coverage, detection of multiple and covert targets, and pinpointing selected ones, thus closing the sensor-to-shooter cycle quicker than ever before. In standoff configuration, the Hermes 900 flies remotely from the area of interest, exploring and gathering information without being detected. In maritime patrol configuration, the system covers large water areas, integrating ISTAR capabilities into the Navy's maritime data network, thus decisively contributing to overall maritime situational awareness.
Okay. All right. So next topic I'd like to talk about is flight control. And, different missiles use different flight controls. It could be a tail control, like a tow missile. A tow, as you know, is a lightweight, inexpensive missile, and that's one of the big drivers is cost for that one. Another missile for short-range air-to-air, like the Python, picked a canard for high maneuverability because of the large off-bore sight that one needs to have for short-range air-to-air combat, dogfights. Another one, years ago with a HARM, we picked a wing control for that one. We weren't so concerned about maneuverability. We were generally going right at the target. And we weren't so concerned about cost. That's a fairly expensive missile, but we wanted pretty good precision. And this provided be able to have pretty good accuracy with small angle attack changes. And that was a part of the rationale at that time anyway. I'm not sure we would do that today, but that was the idea at that time. More sophisticated here, for example, maneuverability in the case of the Iris-T, they use thrust vector control to provide off-bore sight maneuverability. That's interesting. And then in the PAC-3, they have reaction jets available right before intercept, and they're like little shotgun shells that fire, provide very, very precise incrementals, velocities, providing very good accuracy for the end game. And here's one really sophisticated, like the Standard missile, very large missile, has a vertical launch with thrust vector control in order to provide the stabilization you need for the vertical launch, has a tail control for fly out through the atmosphere. And then exo-atmospherically, it's got a reaction jet control for the kill vehicle. So you can see each of those, depending on what you want to do, that's part of the challenge coming up with the best flight control selection. Another thing that missiles do that airplanes and unmanned air vehicles don't is they often fly differently. So here, the most popular type is what we call skid to turn. The missile, if it has either a small wing or no wing at all on it, will typically use skid to turn. And it'll just turn without regard to its roll orientation to go at the target. If a missile has a wing on it, this is a fairly large wing by missile standards, it will use bank to turn. It'll fly like an airplane or fly like a bird. That's more efficiently. A third approach, what they call rolling airframe, it rolls continuously. And there's some advantages of that as far as packaging efficiencies on small missiles. And you only need to have two sets of controls and gyros and accelerometers, whatever. And also there's some cost benefits and whatever. And a fourth approach for exo-atmospherically is one uses reaction jets. This is a very large reaction jet for diverting up, down, left, right. Flies like a hummingbird and has these little attitude control thrusters you can see firing that can kind of point the seeker toward the target. So I've got an example here, video showing these different flight modes. Here's a Sea Sparrow, the vertical launch. Just turns right toward the target. Here's a JASSM. It deploys its wings, and then it's going to fly like an airplane after it does that. Bank to turn. Most missile surfaces are folded on the launch platform to take minimum volume, minimum span. Here's a rolling airframe missile. Here's the bird. This is Edwards Air Force Base in California. There's a facility there for testing those. Okay. All right, talk about propulsion. You've probably seen those aerospace engineers in Sutton's textbook or Leapman and Rajko of specific impulse versus Mach number. And what I've done though is add a little bit to why that changes with Mach number. And if you look at from a specific impulse point of view, the turbine base wins. For military, we have to use hydrocarbon fuel, at least for U.S. military, for Air Force and Army specifically. And what drives that efficiency? And by the way, so definition we hear in English units is the thrust divided by the fuel flow rate or the pellet flow rate. So if this is a high value, that means I can get a high thrust with a small fuel flow rate or propellant flow rate. So this is why you'd like to have a large value for that. But what happens is you go up in Mach number with a turbojet, that Mach number recovery is such, they like to fly subsonically at very high efficiency, but as you go up higher Mach number, Mach 2, eventually Mach 3 or thereabouts, you have to back off on that specific impulse fuel to air to ratio. For a hydrocarbon, typically stoichiometric is about a fuel to air ratio around 7%, a little less than that, in order to not exceed the state of the art in turbine temperatures. So here we have a limit that's really limited more by materials technology than propulsion technology. You can use some exotic materials, you can do some other things, but with the current kind of materials we have today, we're pretty much limited with the turbine-based type systems around Mach 3 or maybe a little higher than that. And so if you want to go, say, Mach 3 or Mach 4 or thereabouts, another alternative would be a ramjet, shown here. Again, typically we have to use a hydrocarbon for that again, especially for the Army and the Air Force to not have observables as far as metal in the plume and whatever. And what constrains that typically is the insulation on the combustor, and there's a material limit that, and so they typically want to fly Mach 3, Mach 4, thereabouts. As you go much faster than that, you got to back off from the fuel to air ratio, just like you mentioned up here. And at some point, you get so low, you have trouble generating thrust, let alone not having good ISP. Good old solid pellet rockets, around 250 seconds for solids. We have to use solids for the military today because of logistics and toxicity and other concerns. We got away from liquids decades ago. And so you can see that is a concern. An intermediate one's called a ducted rocket. It has some of the attributes of a rocket with a gas generator, the fuel rich, and then that excess fuel then does secondary combustion like a ramjet. So as you expect, you have an intermediate ISP. This one over here is a liquid hydrocarbon scramjet. And there could be things limiting its choking and whatever. It can go typically around Mach 6.5 is a typical good Mach number. But even there, at some point, you can argue that's going to be around Mach 8 or so, there'll be some concerns that would limit its capabilities. So I kind of been picking on solid pellet rocket, but to give it a little extra time here, I'll show you an example of why rockets do that these others cannot do. And what they can do is accelerate by orders of magnitude more than any air breather. Just because of physics, and again, I like to emphasize physics-based design, this is the first order of what the thrust is, for example, of an air breather. And I need to have that exit velocity be greater than the free stream velocity to generate thrust. And so you can see if my exit velocity is limited because of state-of-the-art in material technologies for turbines or combustor technologies, for a ramjet or whatever, then I'm going to be limited to a sweet spot where it likes to operate as far as being able to have high efficiencies. In the case of the turbojet, it's most efficient subsonically. In the case of the ramjet, typically from Mach 3 to Mach 4 thereabouts. And then for the scramjet, as I said earlier, somewhere around a Mach 6.5. So this is what the big advantage of the rocket is. I have an example of acceleration here. Back during the Cold War, we had a system which is similar to today's missile defense, except we used nuclear warheads back in those days because we didn't have the accuracy of hit to kill we have now. And the Spartan was kind of like the ground-based interceptor, and the Sprint was kind of like this PAC-3. So let me show you a video of those real fast. This is the Spartan. And that was a sprint. That was fantastic. It was like supersonic at one body length. It had hundreds of Gs at launch. It was very high acceleration. Pretty neat. Okay. Talk here about the, I don't have a lot on propulsion because again, I have to limit my time, but I did want to make a point about supersonic air-breathing missiles. Except for the United States, the rest of the world has a pretty good number of these. You can see here the United Kingdom and France. Russia is arguably the world's leader in supersonic air-breathing missiles. Most of these are ramjets. China's got a couple. Whatever China does, Taiwan wants to do. Here's India, for example. And we in the U.S., we tend to be more oriented toward rockets. And there's arguments for that. Theoretically, if you've got a low observable platform, then you don't necessarily have to have a long-range missile. There's a saying, you don't take a knife to a gunfight. People that do have high radar cross-section platforms, like most other countries have more than us, one thing a missile can do is provide standoff range as well as accuracy. So there's different ways of doing the job, and so it's interesting that we'll see if the U.S. does want to get involved in coming up with a RAN. I happen to be a ramjet enthusiast, by the way. I wish we had some. We do have the Coyote target drone, but that's not really a missile. Okay, I got just this one slide on weight. Again, I wish I had more time to do all this. This kind of shows you that the equation for the thermal tensile stress as a function of strain, and the most popular material for lower temperature would be aluminum. Aluminum doesn't look that great from a strength point of view, but aluminum's lightweight, and so I'm being a little bit unfair in doing that. And then here's titanium. If I need to go a little faster, like maybe out to Mach 4 or so, titanium is a good way to go. If you want to go faster than that, you might have to go to steel or some kind of nickel-based type of alloy or whatever. I'm a real fan of composites, carbon-based composites like graphite epoxy for lower temperatures or graphite polyimide for the higher temperatures. You can save a huge amount of weight because the strength is very high and the density is very low. Now, these are all advantages of that, but like I said, every technology has its strengths and weaknesses. So these all look very good. Hey, this is great, but I always try to be unbiased as I can. We all have our biases, but there's always some warts on any one technology. So you have to look at all those before you make your decision. For example, comparing a composite type of a structure versus say a metal structure. All right. Okay, I'm a fan of the boost glide program as far as these kind of missiles. If you have a missile that's a ballistic missile, for example, exoatmospherically, if one has a satellite or something can do a track file for just a few seconds, you can predict that trajectory, pretty accurately in where it's going to be landing if it's a ballistic missile. If I have a boost glide type of a weapon, that file can change because it's maneuverable, at least endoatmospherically, and it has a pretty good aero efficiency. And so you don't know exactly where it's going to go. It's also its peak altitude will be lower at peak altitude than a ballistic missile. So these radars looking upward may not see it coming as soon as they would see the higher altitude ballistic missile. And also the fact it maneuvers, it can also provide survivability with speed and altitude, and also maneuverability if somebody's trying to shoot it down. So this is something that's come along. China's invested in that. Russia's invested in that. We in the U.S. have sort of had a wake-up call now, and so we're getting interested finally. As I said, I'm a hypersonic fan going back for decades, but it has pretty good efficiencies in flying out, and the things I made these attribute comments already. So let me show you a video here on the boost glide. Oops, I'll try it again.
Sonic glide vehicles are just that. They're a very fast glider.
The way it's launched is they put it on top of a rocket that re-enters, then it flies on top of the atmosphere. It's like a plane with no engine on it. And it uses aerodynamic forces to maintain stability, to fly along, and to maneuver.
Because it's maneuverable, it can keep its target a secret up until the last few seconds of its flight.
The current types of missile defenses are not adequate to defend against hypersonic missiles.
Our whole defensive system is based on the assumption that you're going to intercept the ballistic objects.
A ballistic missile is like a fly ball in baseball. The outfielder knows exactly where to catch it because its path is determined by momentum and gravity.
It's a different scenario. The combination of the maneuverability and the speed makes hypersonic missiles unpredictable and extremely difficult to defend against.
The faster you go, the more kinetic energy you have. In some cases, you may not need to put any explosives on it. The kinetic energy of the vehicle itself is sufficient to be able to cause quite a bit of destruction.
Most countries use some form of what we call an OODA loop when they're making decisions about whether to respond to a threat or not. You observe a threat, you figure out where it's coming from, then decide whether you need to respond, and then act on that decision.
Okay. All right, so moving on, I want to talk now about seekers and sensors. And you've probably seen this before. Klein has a very good reference, by the way, all the way from visible and through infrared, short, medium, long range, all the way down into millimeter wave and radar. Typical missile seekers are typically the order of 10 gigahertz. And as I said earlier here, that your infrared could be long wave or mid range, but you're more likely to have a mid wave seeker just because of the diameter constraint that goes with most missiles. And then for visible, there's not a lot today that's visible just because it only works during the daytime, but that's a possibility with a multi-mode of doing that. One of the problems you have with the electro-optical type, say infrared or visible, is attenuation. Huge attenuation to see here, like 100 decibels per kilometer, trying to look through clouds or fog. Fog is just a cloud on the ground. And so that's one of the problems, is that you don't work very well. You can also have attenuation just due to molecular interactions. The ozone will be an attenuator, water vapor, these so-called greenhouse gases like water vapor, carbon dioxide, will give you attenuation. So you want to operate at the bottom of the buckets. Typically, you'll pick your ranges, like it's a short wave or a mid wave or a long wave, in these kind of ranges where I have to minimize my attenuation. Even millimeter wave will have some attenuation. For example, due to cloud or rain, I picked the typical 4 millimeter per hour rain rate for millimeter wave. And so you can see there's some buckets here where the millimeter likes to operate, let's say 94 gigahertz or 35 gigahertz. Once I get down to say X band or 10 gigahertz or so, the attenuation is not so bad. Okay. And I think I made my points on those already. All right, so this kind of makes a point for radar. But one thing the infrared can do, the radar can't do, is resolution and accuracy. Arguably, the most accurate of all would be like a laser radar. You get really very, very fine accuracy, and also even three-dimensional imagery, which helps you from minimizing susceptibility to countermeasures. This is a Lance missile that was being used as a target, as a ballistic missile. And the Lance missile is being imaged by a 256 by 256 imaging infrared. That's kind of the standard we've been using for years for missile defense. It's like a standard missile 3 type of a seeker. And what's nice about that is I could not only hit the target, because I can see an image of the target, but I can do an aim point selection. If I know where, say, chemical, biological warhead is, I can hit that and try to vaporize those. So that's the thing an imaging infrared can do that the radar really can't do as good. Another possibility is synthetic aperture radar. We've done some developmental work on that. Raytheon had a program called Hammerhead. You can also use it for reconnaissance, you can see. But it's more expensive. It requires a pretty good computing capability, a good inertial capability. And so I don't know of an operational missile that does that, except for some developmental activities. Another one's been in development. Eglin Air Force Base has funded some work by the old TRW, now part of Northrop Grumman at Redondo Beach, of looking at passive imaging millimeter wave. So you're not turning your transmitter on, which helps you from your minimizing your observables. But as you can see here, the resolution is not as good as it would be for an imaging type of a system. But that is a good adverse weather consideration that one might want to consider. Of the videos, this is kind of without going through the video, the SAR type requires having a squint angle, like 10 or 15 degrees, or theoretically be a 90-degree one. And then you get information about the time of return of the target. Not only that, you get the whole ground mapping that goes with all that. So you can use that for reconnaissance. And then at some point, you got to switch out that squint mode into a homing mode. And that's maybe possibly one reason why it hasn't been picked up from an operational. I have a video here. Years ago, I worked on the AIAA-130. We put on a GBU-15 guided bomb. We put an imaging infrared seeker on that and a rocket motor, and also satellite navigation with GPS and also inertial navigation. And that was used in Kosovo with good effect. It was, and these precision guided bombs have really helped a lot ever since the Vietnam War, of minimizing losses of aircraft and minimizing the number of sorties required and minimizing pilots being shot down. So this kind of shows you can see at the beginning of this seeker imaging infrared, you really can't see so much haze, and that's true of most urban environments. There's a bridge out there, but if you have GPS, you can typically get a 3-meter accuracy. So one thing about for missiles that are surface targets that don't move, you don't necessarily have to have a seeker. You can get like a precision accuracy 3 meters with just using a GPS type of a system. But if you want better accuracy, you can switch from that over to the seeker at the end gates. That's what I'll show you here. You can see we're flying out. Here's the crosshairs, and pretty soon you'll see that here's the bridge coming up. As I get closer, again we're flying GPS, and then at some point, this is the tracking gate on the seeker. You can lock the seeker up. This shows you a test of the AIAA-130. Here's the nose of it pointing upward to get lift. And then here's my tracking of the seeker. I'm going after a target in a test environment, and it's homing. One thing happens is called a gravity sag that often occurs on air-to-ground missiles. And that when gravity takes over, you want to compensate for that with some kind of inertial navigation so you don't have the gravity sag. Missiles tend to go blind at very short ranges, and that causes miss distance. Okay, most precision strike missiles are more sophisticated. These are not just US, but international. And for a long-range strike weapon, these happen to typically have a seeker. They've got inertial navigation on board. They've got a satellite navigation system, and they have a data link. And they're typically large and fairly expensive, and so one doesn't mind paying for all those in those capabilities. And this is part of your synergy, looking at how you want to do that in a synergistic fashion. Here's an example here of cruise from an Aero Mechanics point of view. And if I look at altitude versus Mach number, there's a parameter called dynamic pressure. And I'm plotting here from a very low value where it really gets very low aero control effectiveness, and also engines don't work that good. Once it gets down to that range, you're typically high endoatmospheric in that, with a low speed perhaps, but even at a fairly high speed, you're at a high altitude. So going up in dynamic pressure, here's a 500, 1,000 to a very high number. Here's a 10,000, a 20,000 number. Well, if you fly at these very high numbers here, you have very low lift to drag ratio. It's not very efficient. And so typically, if I look at where you want to fly, if you have a turbojet with a wing on it, depends on whether it's a little wing or a big wing. For a small wing, like a Harpoon missile, you'll typically fly around, maybe like around about 500 pounds per square foot. If you have a fairly large wing on it, like a JASSM, and it's at sea level for taking advantage of the survivability of terrain following or sea skimming. If I have a low observable missile, I can fly more efficiently at a high altitude, like say 30,000 feet, high subsonically. And that wing probably more efficiently would be somewhat larger. A large wing by missile standards is small by airplane standards. Typically an aspect ratio of 3 is a typical limit for most missiles in their wings. Now, if I have something that's going to be hypersonic or even high supersonic, that wing needs to get smaller and smaller and eventually goes away. The wing gets in the way if you want to have a hypersonic missile. That's why they're wingless. It does more harm than good. It doesn't really help you in lift wise, and it has skin friction and whatever. So the ramjet here without a wing, it'll want to fly any kind of body lift design around 700 pounds per square foot. That's a good criteria. Here, if I look at a scramjet, Mach 4, 80,000 feet ramjet, scramjet Mach 6.5, 100,000 feet, around the same number. Even a hypersonic boost glide, around 700 pounds per square foot is roughly an optimum dynamic pressure to fly. And these hypersonic boost glides go higher than Mach 7. I just arbitrarily cut it off there. Okay. Talk about countermeasures. That's the most susceptible part of the missile. If you can countermeasure the seeker, if you're an old crow working electronic warfare, you try to get around that problem. When the AIAA-130, that was one of the earlier applications of imaging infrared. We had a one color imaging infrared, 256 by 256. If the threat uses flares, that imaging seeker is almost like a camera. It can see the little flare as a single pixel, and the larger target, which is multiple pixels, it can continue home on in. Where just a single detector would be overwhelmed by the intensity, the blinding intensity of the flare. Even better than that would be a two-color seeker. A flare is very hot, and a two-color seeker can tell the difference between the hot flare and the relatively cold airplane target. So more modern missiles are starting to go two-color imaging infrared. Another possibility would be multi-mode. If you look at, for example, acoustic signatures, a T-80 tank has a different acoustic signature than an M1 tank, for example. Probably not use that as a seeker exactly, but I could use that as a discriminant so I don't hit the wrong target with an imaging infrared. And we had a guided submunition called BAT that did that. Another possibility is another imaging infrared shown here, with the imaging infrared passive, and as well as an active LADAR imaging infrared. What we had with the old HARM missile using anti-radiation homing, the SAM site would see you coming, and they would shut down, and the HARM would go ballistic. So the approach of that with the ARGM is put a millimeter wave seeker on there, active. So when the SAM site shuts down, you turn on your active seeker, and the SAM site antenna is a huge reflector, and so that's been a very effective program, ARGM. Looking at the more modern, the small diameter bomb 2 or the Stormbreakers more recently. It's been a long time coming. It's been a decade or so. They've had some developmental problems, but Raytheon got it right. It's a really challenge of doing a multi-mode seeker of imaging infrared combined with semi-active laser, combined with millimeter wave, stuffing all that stuff in there, getting to work together properly. We've tried, for years we've tried multi-mode seekers, tri-modes, and it looks like this program here is really a go finally. We've had problems with reliability and cost and other concerns, and so I want to give kudos to Raytheon for that program. It looks like it made it. Here's an example of anti-radiation homing and imaging infrared and television. You could use the same optics path for the TV as you use for the imaging infrared. Israel has a little missile. It could be a missile, a one-way item. It's also is used for reconnaissance, flying out, getting information from the visual information from the imaging infrared as well as the television. So let me show you this thing. It's actually propeller powered. So what's happened in recent years, now that the Cold War is over, we've invested in these unmanned air vehicles, and they do what they call DQ, the dull, dirty, and dangerous jobs. And hopefully pilots don't get shot down, and they're like a fraction of the cost of an airplane, and yet they have lots of good sensors on board for doing reconnaissance or even being a weapon. Okay, they'll have a little bit on warhead here. And one thing we've done in recent years, the Cold War is over. During the Cold War with these huge warheads, and we have fewer assets available now and we're trying to make more with less. So there's a good argument to have small, lightweight weapons if they're effective. And here I give some examples here of the if you get high lethality, and there's some warhead technologies you want to look at to do that, and keep the weight down. And there's also low collateral damage, which is more concern now the Cold War is over. So here are examples of weapons are going up to the size of their warhead, which require accuracy. The Bill is a Swedish weapon that has an explosive form projectile. It's a very lightweight, 1.5 kilograms. It flies over the tank and shoots those projectiles right through the hatch of the tank. And a small system can take out a mean battle tank. Something a little larger than that is Roland. It's a 9-kilogram warhead. And this is more of a cylindrical type of a pattern. And the energy is a little more, wider. And so that, but for at least air targets, that's normally not a problem for collateral damage. Might be for surface target. Here's one, for example, has a jet, a shape charged jet, and but also even that, because that warhead case fragments. Here's an 8-foot high witness plate. You can see there is some potential collateral damage, as I'll show you in a little bit. And here's one that's fairly large by today's standards, small by Cold War standards, is a guided multiple launch rocket system. And here it's going to set its warhead off and against the target. So I'll show you a video showing here going up and the concern about collateral damage as well as effectiveness. By the way, this tank is a robot. No humans were harmed in making this video. You can see if you get inside of a tank, bad things happen. There's ammunition, there's fuel, there's all kinds of stuff inside the tank. So pinning the training to tank is the key thing. And top penetration is easier than the glacis, than say going head on. So a lot of the missiles will try to go for the top because that's a way to take out a main battle tank. That's what the Javelin does, for example. Okay, here's Roland. You can see it's going after a drone target, and that target is maneuvering pretty good, and Roland is staying right with it. It's a pretty maneuverable missile. Roland was a joint program with the French and the Germans, and they wanted to find a common war hero they could agree on. They had to go back to mythological times, Roland, to get their common war hero. Here's a Hellfire. It's a 4-foot by 4-foot target board at Eglin Air Force Base, and we've shot hundreds of those, and it always hits the target board. The most accurate of all is semi-active laser guidance. It's very, very accurate. You always hit the laser spot. But you can see there's collateral concern here. Even though that warhead, 24 pounds, it's so the last was that multiple launch rocket system with a 108-pound warhead. So you can see why today we're interested in collateral because of civilian proximities and a lot of things we're doing. Okay, talk about survivability. In the video, you heard about these hypersonic boost glide, speed of survivability, altitude survivability, maneuverability, survivability. And these things are just unstoppable, and so it's something that everybody's all concerned about right now. One been around for years is the Russian Sunburn, very high altitude and very high speed. If you're a ship captain, that's like your worst nightmare, is a sunburn coming at you. Here's another one. Russia, as you know, has lots of anti-ship missiles. This one has an efficient flyout with a turbojet, and then for the end game, it stages a rocket that penetrates at supersonic speed. So those are more classical types. And then for reduced observables, there's naval strike missile. Years ago, I gave my short course at Kongsberg, and it has features for that. It has a faceted dome. The radar bounces off that rather than coming back because it's a flat surface. It's got a serpentine inlet that basically the radar gets in there, bounces around a bunch before it comes back out, reducing it's got a T-coupled airframe. You can see there's a roll bearing here. And during the flyout, the inlet is on top. I'm sorry, it's on the bottom, I'm sorry, for efficient cruise. And then for the end game, it'll switch over to the top so the radar on the ship or what you're going after can't get a direct access to the inlet. It's got body chimes. Anytime you see a missile with chimes on it, you know they were worried about radar cross section. And then it's also graphite. Graphite or carbon base will reduce the signal electromagnetically about 10 dB just to changing that into heat. US has a similar system called the JASM. Talk about the safety, I have a video I'll show you here in a second here. We're big on insensitive munitions. That's something that was kind of a wake-up call due to this event I'll talk about a little bit. But so all missiles have to go through this now and be qualified. We weren't doing a good job at the services and the contractor level, and so the Department of Defense put that on a high level that thou shalt do these live fire testings. Things you're mostly worried about is the propulsion system, propellant and fuel, and the warhead. Those are the two most energetic things. There are other things too, but those are the two most. And so what you want to do is if I'm going to release that energy in an unplanned fashion, like I get hit by a 23 millimeter or something of that sort, I prefer to burn. That means there's less power involved. You know, the energy is going to be there, but if it goes over a longer period of time. As you go up here, this becomes more and more of a concern. You know, you go from a deflagration to an explosion like a millisecond, to a partial detonation, to a detonation like 2 microseconds. That's what you want to avoid. So here's the MIL standard. You got to test it against all these events to do all that. And that's a challenge because you don't really know for sure you're going to pass until you get the full missile available pretty much at the end of the program. So let me show you this wake-up call on the Forrestal. I'll set it up for you a little bit here. Vietnam War is going on, 1967. We've got an aircraft carrier here, the Forrestal, and the aircraft have landed. They're being refueled and being rearmed with bombs. You got an F-4 over here, and the F-4 had a power surge, and the power surge got through and set off a Zuni rocket. That's like an unguided sidewinder. Shot across the deck, hit an A-4 in the fuel tank, and the A-4 caught on fire. John McCain, by the way, was there. It wasn't John McCain's airplane, but he was nearby. And then that fire started, and then these bombs started going off. So now the sailors are starting to fight the fire, but there's a bomb that goes off, and it drives them back, and some of them are literally on fire. They're burning. But these guys are real heroes. They turn around and go back to fight the fire. As I told Walt and Chris the other day, that you know, in the Army, every soldier is a rifleman. Even the cook has to know how to shoot a rifle if you get overrun your position. For the U.S. Navy, every sailor is a firefighter. Your worst nightmare is a fire at your ship, you know, at sea. Here's another bomb going off. Drives them back again. Here's another one going off. Here they're pushing perfectly good airplanes overboard just because they have fuel on them. You do what you have to do. That event cost more loss of U.S. Navy lives than any event since World War II. So that's why we're so serious about that. So you've got to do insensitive munitions for any kind of new missile you're doing today. Okay, talk about the constraints in carriage. I show you here some typical large missile types like surface ships. Vertical launch systems are standard. A typical box launcher, pretty much set up for the old Tomahawk missile, its length and its weight and its diameter. The submarines have a similar kind of a system for canister launch for the Tomahawk. They've got also the big boomers, the ballistic missiles, the Trident, and also they carry harpoons, which are launched horizontally out of torpedo tubes. And these are the constraints that go with those. So much smaller are fighters. There's no real hard requirement, but typically like a bomber, the length limit and a typical weight type of limits and size are pretty much there. And then for ground vehicles, shown here, the ATACMS and the multiple launch rocket system, I mentioned earlier, typical constraints for those. That's the kind of a standard for the Army. Helicopters and small unmanned combat air vehicles, they're very constrained. The Hellfire is a large missile by their standards. And the most constraining of all would be your gun launch systems, tanks, artillery, ship guns. Here's an example of a 120 millimeter, for example, typical constraints. So you need to be very much aware of that. That's one thing the missile designer has to do. You cannot change the launch platform typically. You live with that, you live with the fire control, and you have to make do with that, where people designing airplanes have more freedom typically. Okay, example of fire control interface. I picked the Patriot, you know, has radars and power and antennas and launchers for both the PAC-2 as well as the PAC-3. So that system of systems have to work together. Typical guidance alternatives in the autonomous guidance is popular with the US. Either has an active seeker on there, like the radar seeker, or will passively home on emitted energy and infrared energy, for example. Each of these has advantages and disadvantages. Some active, like the PAC-2, for example, the fire control, similar with tracked via missile, tracks a target and that reflected energy, it could be radar, it could be laser, and it homes in on that. And that has some advantages as well as disadvantages. A third approach would be command guidance, where you have a smart fire control and a dumb missile. The fire control tracks the target, tracks the missile, and it sends commands to a little rearward-looking sensor that the missile gets told where to go. Obviously, cost is a big driver for that type of a system. In the case of this one here, a launch platform survivability is a driver because of the, once I launch it, I don't have to emit anymore. And down here, the fire control is active, so that's a concern in the launch platform survivability. But this one being a high power, you can do more likely a lock on at launch with your missile. For this one here, the missile's got to fly out for a while because it's small, low power seeker. And so that each has advantages and disadvantages. But what I'm a fan of today is multi-mode guidance. And so you have a seeker that's augmented with an inertial navigation system and a data link for regrets avoidance, so you don't accidentally shoot down a friendly or a neutral. So pretty much modern missiles, at least by US, are more and more becoming multi-mode guidance. Here's an example, for example, of inertial navigation with a data link and a radar seeker. This would happen to be United Kingdom. The Meteor, which is like a follow-on to the AMRAAM with a ducted rocket, has more than double the range. Here's an example of the Brimstone inertial navigation with a millimeter wave seeker guidance. Here's the PAC-3, for example. So those are all examples. Let me show you a video here of the PAC-3. I guess let me check with Walt and Chris on that. We're running behind schedule. Do I need to shorten and maybe eliminate some videos, or should I plow on? It looks like I'll probably be another, I'm predicting I'm going to be another 20 minutes. What do you think?
You're fine.
Am I okay? Okay. Let me show you the video. It's a good video. And I know you people, you Lockheed people in Orlando, even though this is a VOP type of a concept, that it will be of interest, I'm sure.
The basic Patriot air and missile defense
I'll turn the volume up.
includes a fire unit, which includes a trailer-mounted Patriot launcher capable of firing 4 PAC-2 missiles or 16 PAC-3 missiles, an engagement control station for battle management, command, control, and communication, and a Patriot radar. The PAC-3 missile weighs about 700 pounds at launch, is approximately 17 feet long, and about 10 inches in diameter. The PAC-3 missile uses a solid propellant rocket motor, aerodynamic controls, and attitude control motors, ACMs, during flyout to the target. The ACMs are small, short-duration solid propellant rocket motors located in the missile forebody, which fire explosively to refine the missile's course during the end game of the flyout. In a typical scenario, multiple Patriot fire units would be deployed to provide overlapping coverage. First, the radar electronically scans the skies with close attention to the horizon, searching the entire volume with overlapping pencil beams. 2 targets are detected: a tactical ballistic missile coming in over the horizon and a low-flying cruise missile. When the targets are detected, the radar communicates with the computer in the control station and immediately schedules more frequent beams to the target in order to confirm and establish tracking. The tracking data is passed to the Information Coordination Central, or ICC, for correlation and validation. Targets can be tracked manually or automatically if so desired by the operator. However, the operator always maintains override capability, able to change designation from hostile to friendly. If and when appropriate, the system or the operator will engage the hostile target. An Engagement Decision Weapon Assignment, or EDWA, is made, and the now determined hostile target is assigned to the optimally located fire unit. The engagement sequence then continues at the fire unit engagement control station level. During the engagement, the system computer determines the optimum moment for launch, transmits an initial heading instruction to the PAC-3 missiles, then gives the command to the launcher to fire. Per current operational doctrine, 2 PAC-3 missiles are fired at each TBM target to maximize the single engagement probability, ensuring protection of the high-value asset. The missile flies via inertial guidance to an intercept point specified prior to launch by its ground-based fire solution computer, which is embedded in the engagement control station. Shortly before arrival at the intercept point, the Ka-band seeker on the PAC-3 missile acquires the target. An optimal aim point is selected, and terminal guidance is initiated. The combination of a precise seeker and an agile airframe enables the PAC-3 missile to achieve hit-to-kill intercept of the target. Direct body-to-body contact of the missile and the target creates very high energy, which facilitates destruction against advanced theater ballistic missiles, cruise missiles, and hostile aircraft. Most importantly, it destroys weapons of mass destruction carried by the warheads. Once the battle manager has determined that the threat target has been defeated, any remaining PAC-3 missiles in the air are issued a command to self-destruct. PAC-3, hit-to-kill superiority, combat proven.
Okay. I spent a fair amount of time on seekers because that's the most expensive, typically the most complex dissipated part of the missile. So that's why I want to give more time on that. Talk about climate and your environment of what you might want to consider. A first order would be at a 1% probability extreme. And US, we do expeditionary warfare. And so typically I look at the temperature spec, it's a pretty broad one. That's particularly a challenge for the rocket motor. Rocket motors aren't happy at either very high extremes or very low extremes. Sometimes you go very low. When we did the SRAM missile, for example, we were storing those in Thule, Greenland, and we qualified that rocket motor for minus 80 degrees Fahrenheit, which cost us a fortune to do that job. But you typically don't want to go to the worldwide extreme, especially at least for tactical missiles, because of the cost and probability of doing that. There's other considerations. What is your probability? You have a reliability probability. There's others too. But that's a typical specification. But it's up to the contractor and the government to get together, decide for a given missile. When we did the Hellfire missile, it's a relatively cheap missile. We picked a minus 40 degree Fahrenheit to plus 140 for Hellfire. So it all depends on what you're doing. But here's different specs that one might consider. And the wind, what's the likelihood you're going to do combat in the middle of a tornado, for example? These are all considerations. You get surprised every now and then. We did Desert Storm. We had designed our systems, for example, the filters on our combat vehicles for a given spec that was sort of based on, or thought based on, kind of like the environment they were used to pretty much in the Cold War, in the Fulda Gap or whatever. And of course, the desert, you have a lot more dust. And so we had to go back and redo some things to fix up some, every war is different. Anyway, so these are all examples. I wanted to show here this example here of the typical ground environment. It's oriented mostly toward ground with a little bit of a sea environment also. And it's oriented toward Army type systems. So here you've got ATACMS and multiple launch rocket systems being fired. You can see there's dust, there's shock, vibration. Here's the HIMARS. We've switched from the treaded type vehicles to the wheeled type in recent years. Those are more logistically friendly. You can put those on C-130s easier and whatever. By the way, years ago, the old Martin Orlando, where you are, used to have a facility that they would test those things in. You can see the shock and vibration that's going on there. Here's C-130 with a HIMARS. Okay, here's a multiple launch rocket system coming out in slow motion. You can see you've got the plume, you got the shock, vibration, temperature. So the missiles behind are being subjected to an environment. So that's part of your qual program, is you want to make sure that the that you're going to be able to operate without any real problems. Here's a vertical launch system. It's tough to load. And one time we thought we'd try reloading at sea, at least a fairly low sea state, but that would take up some cells and whatever. And so pretty much today we just loaded in port. But what happens is the hatch opens up and then the missile comes out vertically. This happens to be a standard missile. You can see the missiles behind that in that cell have to contend with that temperature and shock and vibration environment. Here's a submarine launch of a Tomahawk flying through the water with a jet tab thrust vector control. Then it's going to break water with the booster. And then the booster will drop off when it gets to a minimum Mach number, and the engine will take over, and it'll fly with the turbine propulsion after it gets up to speed. All right, so that's part of your qual program. I think I made all those points already. Okay, talk about the activities and development, and this kind of shows you kind of like your simulation, what you want to consider. The heart of the simulation is the guidance and control. That what's make the missile accuracy is one of the reasons you want a missile, and then the other reason is range, compared to say a gun launch system without guidance or free flight or a bomb or whatever. So these are the system components of the guidance control: the seeker, the actuators, your flight controls, sensors, gyros, accelerometers, etc. And first of all, start with just a digital simulation with analytical modeling. As I get test data on those, I will feed that into my digital simulation. It'll get better and better. Same way with the aerodynamics, as I get wind tunnel data compared to the prediction, I'll improve it. Same way they do propulsion testing, rocket motor firing, or engine testing, whatever. You'll update your digital simulation. And then eventually you do hardware in the loop. That will be real hardware that I will update that also and carry those. These two simulations go pretty much for the whole program, for the life of the program. Environmental testing to show you can take the environment, loads testing, the things that are hazardous like the warhead, you'll do separate testing of those. Eventually you want to do a flight test. I wish we had more money for flight tests now, but we used to do a lot more of that. And we get surprised anymore because we don't do enough flights to get statistical confidence. But you'll start off fairly straightforward and work your way up, looking at the launch platform integration, carriage finally, and then separation, safe separation, especially from an aircraft. And you do guided flights, you'll take the warhead out and have telemetry in that section to try to get some data to correlate. And eventually have a live warhead firing flights with the warhead being active. So that's kind of how one would do your development. These are example facilities. Here's a wind tunnel facility and a French wind tunnel facility of a ramjet. The French, by the way, historically have been very good with missiles. They've had a lot of leadership activities in that area. Here's thrust vector control, for example, with a rocket. Here's a direct connect test. Again, Martin Orlando years ago used to have a facility we tested in when we did a missile, a ramjet missile called ASOM, with a direct connect test. A lot of those facilities, unfortunately, were closed down when hypersonics sort of went away in the 80s and whatever. And I'm glad to see hypersonics coming back. That means we also need to invest in our facilities to bring those back online. Here's a free jet, which is more sophisticated, has the inlet included. Here's a warhead being set off. You got these witness plates that measure the spacing and the holes and whatever in the warhead. There's a static firing. Here's a sled test of the warhead. Dynamically, warheads are different if they impact, different dynamically than statically. Here's an IM test. You can see it's not a happy airplane. that missile exploded there, and that's an expensive thing to do, but you want to know if that's going to be a problem or not. Here's a loads test. We normally don't do loads testing on tactical missiles except for cruise missiles. This is a South African cruise missile. We do sometimes on strategic missiles. Well, we always do it on strategic missiles. And sometimes if it's an important tactical missile, like PAC-3, for example, had a structure test. Here's a secret test, anechoic chamber. Here's a flight table test of things that are rate sensitive, like gyros and accelerometers and your seeker tracking. Here's environmental test here. I was saying the other day to Walt and Chris, in Florida, the McKinley Chamber at Eglin Air Force Base is the largest in the world. They can test full-scale large aircraft there in that facility. It's pretty neat. You get a chance to tour Eglin. They have some really great facilities there. Here's the submunition dispenser test. And what's happened in recent years, not only simulation, we sort of believe our simulation, and that's the argument for maybe not doing as much flight testing. But we're also really believe our analytical tools, finite element modeling, computational fluid dynamics, and whatever. But we still get surprised. And for example, here, the submunition here is dynamically, and it's got M on N interactions. So you tell me, with all those mutual M on N interactions, how can CFD really do that job? CFD does a great job. It's much better now than it was 50 years ago, but you cannot eliminate wind tunnels and you cannot eliminate flight testing. I think we're naive to think we can do that. Here's radar cross-section. This is a JSOW in an anechoic chamber, full scale. Here's a integration of of the avionics, and similar thing you do if you had a combat vehicle integration testing with the fire control. Here's a flight test of a French missile doing a high performance maneuver, kind of like you saw the Sprint years ago, using thrust vector control. So I've got a video here that kind of goes through that. First one here is, as I mentioned, I was on this program, the AG-130. You get surprised in the wind tunnel. We thought we could slap a rocket motor on the side of a GBU-15 bomb and triple the range. And we proposed it as a firm fixed price contract. We proposed doing that in 3 years as low risk. And it ended up, as a contractor, it cost twice as much, so we had to eat the cost. It also took twice as long. It took 6 years. It wasn't a trivial problem. One example, for example, was this bomb on the side. When we deflected our control surfaces into the bomb, we choked the flow. And so we had different flight control effectiveness depending on which way we deflected our controls. It was also not axisymmetric, and we didn't quite get good modeling of those asymmetric forces and moments. And also this rocket motor is longer than we really had experience with. And you find that rocket motors have very high fineness ratio, very long lengths with small diameters. They tend to blow up on you because of resonance occurs with whatever frequency. So there's always lessons learned. Anyway. Here's store separation testing. I'm sorry, I got checking my notes here. Here's a rocket motor firing. You can get plume information in addition to basic force and moment data too, which is kind of neat. That's almost for free. Here's a vectoring test. Here's a hover test. Here, propellant, they're mixing up, it's almost like making bread dough. And one thing you want your propellant to be is flexible, because you got to over a wide temperature, let's say minus 60 degrees Fahrenheit. You want to make sure that it's going to be flexible. Here's a scramjet trying to get thrust equal drag. Here's a witness test of the warhead arena. Sled test of a warhead. Here's the penetrating a warhead. See, it did pretty good. It went through that concrete, didn't break up. Here's an IM test. They shot that, and it's doing pretty good. It's just burning, no big deal. And then they put it in a fire here in the next one, and not so good. It exploded. That didn't pass. Here's a flight table for simulation, seeker, accelerometers, and gyros. Here's devices that are used, deploying the fins, the wings on Tomahawk. Lots of explosive devices on a missile. Kick off the rocket motor. Here's a environmental test. You can see we got some problem here. We got some icing on the dome. And here we're shaking the ice off the jet vanes, thrust vector control, and the fins on the AIM-9X. This is a dispenser test. Here's avionics integration. This is at China Lake. China Lake has a very good capability as a government organization. They've done a lot of good original work. They're all good. I enjoy working with Huntsville, and I used to work at Wright-Patterson, and I work with the Navy, also Dahlgren. Here's a pit test, store separation, and here's that vectoring I mentioned of the French missile, the Aster, showing high maneuverability. Here's a gun launch projectile at Aberdeen Proving Ground by the Army in Maryland. Guided projectile. Just dispense the sabot. So as a program manager, you have to decide, how much testing I'm going to do. Do I have the right facilities? Do I have enough money for it? Does it fit the schedule? And you got to back that up with analytical. And that's one of the more interesting things to do, putting together a program that'll do the job with minimum cost and a short schedule. Okay, I'll give you a little bragging here about this program we worked on years ago. Orlando did the aerodynamics and propulsion working interfaces, and Raytheon was the lead contractor, and they were worked mostly with the seeker for that, called the ASOM, Advanced Strategic Air Launch Missile. It was interesting when you all looked at the long-range anti-ship missile. That was one of the competitors potentially, but as I say, we in the U.S. we seem to be more oriented toward low observables, and so we ended up picking something that was not a high-speed missile, but more of a conventional low observable type with turbine-based propulsion. Anyway, this demonstration I want to brag about is that we did this in 7 months. We did 7 shots. We'd spend 2 weeks planning our shots. We'd shoot it, spend 2 weeks analyzing the data, replan it. We did, a shot a month, basically, in spite of the fact we were 0 for 2 on our first 2 shots. That first one, as a program manager, you don't want to do anything really crazy. So we kind of launched in the middle, or started our engine, ramjet in the middle of the flight envelope. And that was okay, but we had a hard-over failure on our fuel control. And so we broke through our barrier of high dynamic pressure, and we flew for 60 seconds. We broke the world speed record, which still stands today, Mach 5.6. There's never been an air-breathing missile that's flown that fast in the last 40 years. Even the X-51 didn't fly that fast. And then the second one we tried, we had a hardware failure on our flight control, which is often things that fail. So we're 0 for 2, but we were a bunch of cowboys back in those days. We had a lot more freedom, and they didn't shut us down. Today, they probably put you out of business for months, maybe even a year or longer. But we just went on, and our third shot, we went for broke here. We explored the high dynamic pressure area boundary, went up here, and we cruised at Mach 4, 80,000 feet to see how efficient we were, and we flew for a pretty long period of time. We did a bunch of other shots looking at the transition from rocket to ramjet, make sure that we get enough thrust to accelerate. That's historically been a problem for ramjets. And but that was a great program, and it was not an engineering development. It was strictly just an advanced development program in doing that. But it was a fun program to work on. You guys did a great job at Martin, by the way. Okay, talk about missiles, what they've done, and interest time. Maybe I won't spend too much time on these. Where we were compared to, say, back in the Cold War. Where we are now is a lot better off. Much of that due to the electronics and the sensors area, and to some extent the propulsion area. But these are things that have happened. As you might recall, the SA-2 shot down Gary Powers and the U-2 and that was a wake-up call. One of the earlier demonstrations of China Lake being a lead was using portional guidance. This is the initial operational capability, by the way, not necessarily the demonstration day. This is the first beyond visual range intercept that was done. If I look up here, these are some other things that happened. There's a technological surprise, a thrust vector control from the Archer compared to the old Sidewinder, which led us in a crash program to the AIM-9X. PAC-3 demonstrated hit to kill with the radar seeker endo-atmospherically, exo-atmospherically and high endo standard missile. Standoff range over that of the AMRAAM has been demonstrated by the Meteor. There was an ICBM race we had with the Soviets at the time. And it's interesting that Soyuz ICBM type is still providing US rides to the International Space Station. I'm embarrassed for the United States. For a while there, we didn't even have the capability to get to the International Space Station when we shut down the space shuttle. Early application of aluminum, which you need to have. You cannot use liquids on submarines. It's very hazardous. And that was Admiral Rickover had a great program to do that. Guided bombs saved a lot of pilots' lives, a lot of reduced the sorties, and had great effectiveness in Vietnam. These are just a bunch of other things that I just probably shouldn't spend too much time on. But there have been a lot of things we can do today that we could not do 50, 60 years ago. Okay, this is designed to be an eye test. If you look at all these are all technology options for different subsystems. Think about those if you're doing a new missile program. Each has advantages and disadvantages. And that's all I have. I apologize for running late. I'm about 20 minutes later than I really hope to be. But I appreciate any comments and questions. We're going to be open for questions here. And then also comments and also data. This is all public release, unclassified. So if you have some information available to complement this, I never like to get the same presentation twice. I appreciate any kind of information you might have. As Walt mentioned, here's my email, and also I have a website that's available. You might want to take a look at. So I'll let you all handle the Q&A here, and I'll be glad to answer whatever questions you all may have.
Okay. Well, I had a question. It's a comment. I was just in a presentation today on your slide number 27.
Should I go back to that?
Yeah, go back.
Got it. All right.
Okay, so right there, you got model digital simulation. Well, with this digital thread, systems engineers are getting to integrate. You're starting to integrate all the Aero models, propulsion models, and lab tests and all that.
Right.
But from the system engineer's point of view, there's a lot of other things going on, like maintainability, risk management. There's other things that are going on that we're starting to do what's called model-based systems engineering, which is model-centric. So you seem to be headed in that direction here with your digital sim.
Good point. Yeah, so yes, these system engineering considerations of the launch platform and the fire control and all those things, as a system of systems, I tend to be an old school person, and so we were always computer limited in what we could do in our modeling. But today we can do so much better, even with desk, PC type based models. We can look at things today. Also, want to put a plug in for Georgia Tech. That's historically through the years, Dr. Mavris's organization has done a lot of great work in looking at those kind of integration considerations and the model-based simulation and whatever. So some of the schools that are especially system engineering oriented, you mentioned University of Texas, Arlington, and others, are very good at doing those kind of things also at universities. And of course, the contractors now are doing it also. Thank you. Any other comments or questions?
Yeah, we have a few from our YouTube chat. So if you're watching on YouTube, if you have any questions, make sure to type them in the live chat on the page. If you're not logged in, I think you do have to log into YouTube in order to chat. So that might be an issue if you're not logged in yet. So we do have a question from Shane. He says, first off, thank you for the talk. My question is regarding the U.S. and hypersonic missiles. You mentioned that the U.S. has very little or no scramjet missile. If that is true, and how does the U.S. compete with other countries? I rarely ever hear of the U.S. being behind in something.
Yes, as a matter of fact, I worked at Boeing. I was for the Seal Beach part of Boeing. I was director at the time for hypersonics, and that was one of the things that Boeing was big on. Both the Seal Beach people, the old North American heritage, which goes way back to National Aerospace Plane. Kevin Boca was in my organization. Some other people that are well known, Marty Bradley and others who work in that area. And then McDonnell, George Orton also had a similar kind of thing. And we were working on a so-called pure scramjet type with Pratt & Whitney, was our major subcontractor, of looking at that and developing that. And there was money for that for a while. But seems like, boy, you know, in the late 1990s, it just money went away. And then same way in the case of the St. Charles, Missouri, with George Orton's organization, they were working on dual combustor ramjet and scramjet, and each of us had different approaches. But that time, Boeing, we thought we were so great. There was a press proposal came out from DARPA of looking at a design study and a demonstration program and scramjets, and they're going to give 2 awards. Well, if you're a contractor, one of the tenets is you never compete against yourself. But we decided we were so great in scramjets, we're going to turn in 2 proposals. We did. We had a Seal Beach proposal, and we had a St. Charles proposal, and we got both contracts. And I had grumbling from Raytheon and Lockheed and Northrop Grumman, whatever about that, But Boeing, in pursuing the scramjets, and by the way, also the people at St. Charles also was very good in hypersonic boost glide. Also, we had Ed Eisworth and other people that are working that problem, as well as maneuvering reentry vehicles. But it seems like the money's it's gone away for the U.S. to do those kind of high-speed things, and I think part of it's cultural. Like I said, we in the U.S. decided to invest in the F-22 and the F-35 and these low observable launch platforms, and then the Navy's invested in lower radar cross-section ships and whatever. And there's less money involved. And you know, theoretically, if you're an invisible hand, you can terrorize the whole room with a hat pin. You theoretically don't need to have a long-range missile. Theoretically, if you're worried about survivability. Of course, that long-range missiles do other things about protect the launch platform. They also have a job to penetrate and get the target out, which is like this boost glide we talked about, which is more difficult for people to shoot it down. But in any event, we kind of fell off the wagon there, and I think it's kind of a wake-up call with the Chinese and the Russians now that we're trying to catch up. And one of the problems we have with the scramjet is kind of a technology looking for a home. It's, as I say, from a physics point of view, the scramjet is going to be thrust limited. It's going to be more of a point design. And in the military world, you never want to be predictable. And so that's what makes the boost glide so challenging, unlike the ballistic missiles, which are predictable. And that's been one of the, and also there's technology problems with the scramjet. Get the engine to work right. The scramjets tend to be very long combustors. You're trying to do supersonic combustion. And the technology's been a challenge where the ramjets, which there are those out there, are a more straightforward solution. But like I said, every time I've seen the U.S. come up in a new follow-on program, like we looked at a follow-on to the SRAM one time, and we compared a follow-on possible rocket-powered versus the ramjet. In the U.S., we always seem to be like a rocket mafia here. They don't seem to want to go that way for some reason, except for Boeing and a few contractors. But most contractors are typically more oriented toward the rockets and the government too than they are toward the rear. So I think it's partly political, partly technical, but other countries have gone ahead and done that. Even India, India is very proud of that Brahma. Now, of course, they had some Russian help in developing it, but they did a lot of the stuff themselves. And so it's something that I think we should have my opinion, a more balanced approach of working these air breather hypersonics and high supersonics and doing our work. But I don't know if that answered your question or not, but I think that's part of the rationale.
Thanks. We also have a comment from a little while ago, as Andrew Fritz from Georgia Tech said he can't stay through the end, but wanted to say he enjoyed the presentation.
Yeah. Andrew's one of my former students, by the way. Okay.
Great.
And today's his birthday, by the way, also. Happy birthday, Andrew. He's with Raytheon, yeah.
Melvin says, thank you for your time today. The question is, what are some typical max L/D and max angle of attack values for hypersonic glide vehicles? Yeah,
good question. If they're hypersonic, they're not going to have a wing on it. If you have a wing on a missile, as over pretty far range, and my short course deals with more of that. If the wing and local angle of attack, and also applies to surfaces, is typically around 22 degrees, it'll stall. But as you go to a lower aspect ratio, it'll tend to stall at a higher angle of attack and whatever. But the hypersonic systems don't have wings, and so you can take those up to higher angle of attack and get good L over D. But the L over Ds are such that it is true that the L over D max that would go with those. I tried to show you theoretically the maximum that you probably could do is the way you get it is with a non-circular body. You know, a circular body will have a fairly small L over D. As I go elliptical, 2 to 1, 3 to 1, whatever, you know, maybe even greater than that, like 4 to 1. But first order is roughly proportional to the ellipse that you have. So you can get L over Ds of 3 to 1 with a lifting body. The maximum probably is maybe something less than 4 to 1. So yes, compared to an airplane or whatever, it's not going to be as high. But if you were to try to put a wing on there to make it look more like an airplane, you do more harm than good. It would actually take it away from the L over D. But even an L over D, you know, first order in a glide system, again, I try to show that in my short course analytically. In a pure glide, it's essentially constant dynamic pressure, and hypersonically, you're essentially independent of Mach number, your aerodynamics. There's not much influence on your coefficients. Then it's proportional basically to that L over D. So if I can get an L over D of 3 to 1, I can glide 3 times as far as an L over D of 1.
Thanks. And I believe it's Viraj. It says, in terms of traditional guidance laws, I'm generally familiar with proportional navigation that uses line of sight rates. Are there newer guidance laws or schemes for modern missiles?
Okay, great question. And there are. I'm going to be a little bit sarcastic here, if you don't mind. The more modern guidance laws are great for a PhD thesis, okay? But the problem we have is pretty much today's missiles are typically modifications of proportional guidance. The problem with the more modern, like for example, one of the more modern guidance law is the sense acceleration. So if I have proportional guidance, it's based on the target being sort of cooperative of maintaining a constant velocity and maintaining a constant heading. And then my missile then sets up its velocity and heading to provide the triangles required for that intercept. I talk some more about that in my short course. If I know something about the target maneuvering, I can do an extra prediction on that. The trouble with that to some extent is a couple of reasons. One of which is acceleration is very difficult to measure with any real kind of accuracy. So that measurement is very noisy relatively compared to say measuring velocity or predicting velocity. And then also also you're more susceptible to countermeasures. As I said, when I had the Aircraft Survivability Group organization at Wright-Patterson Air Force Base, we trained our pilots on maneuvers against missiles coming up at them, you know, whatever they happen to be, you know, SA-2s or SA-4s or whatever. And so the pilot would know when to do a high G maneuver at the right time, and that missile would skid right on by. Now, if you had that modern guidance law that said, okay, that theoretically that'd be a good idea, I'll put some extra maneuverability to account for that maneuver. The thing is, the pilot can do a switch over maneuver and go the other way, and you outsmart yourself. So you're susceptible to countermeasures. And another problem with these modern guidance laws, they typically use Kalman filtering. And Kalman filtering, you need enough time events to occur to filter that out. That works very good for inertial systems, like, you know, say combining the GPS with INS, satellite navigation with inertial navigation, because you're flying out and you can basically do a good job on that. But events that happen very quickly, like terminal guidance, you're talking about seconds or fractions of a second, perhaps even, then that's a real problem of being responsive. So that typically, I didn't make that point exactly, but typically our missile defense systems, say exoatmospherically, they use strap-down imaging infrared seekers. Those are lightweight because they don't have active transmitters on them like a radar would have, but they have high resolution, and they use reaction jet control thrusters, which are very precise, and there's a low noise in all doing that, and that's how you can get hit to kill. These other things you type of do, once you induce noise, you aggravate your accuracy, and also you become more susceptible to countermeasures. So, a matter of fact, I had the privilege of knowing Holt Ashley at Stanford. He was like a Renaissance man as far as not just missiles, but in general. He knew propulsion, he knew aerodynamics, he knew flight control, he knew structures, he knew everything. He was a great professor, and he has a really excellent book out on optimization. And he makes fun of a number of areas, include optimal guidance, about how we often outsmart ourselves, being great for PhD thesis, but from a practical point of view, quite often it's not very robust. And so you may have a point design as optimum, and just a small deviation from that point design, you fall off the cliff as far as having any kind of accuracy. Matter of fact, put a plug in again for Georgia Tech here, Dr. Mav's organization. With the more modern computers, you can do robustness analysis and run, a bunch of things, Monte Carlo schemes or whatever, to see how robust your answers are. But typically, that's what's good about proportional guidance. It's there in Mother Nature. If you see a cheetah running down a gazelle, it automatically does that as a lead. If you see a safety running down a fullback before he hits the goal line, it's instinctive in doing it. That if you see ships trying to avoid themselves, if you're on an entrance ramp on the freeway, you look over and there's a big old truck over there, and you go down, you keep that, and your angle looking at it stays the same. You instinctively know you're on an intercept course with that truck. So it's a very robust thing. It's been around for millennials, and so it's typically some modification to it, maybe not necessarily pure, but if I can sense certain things, if I have a seeker on board that can measure the target velocity and the target aspect, and I know my own velocity and my own aspect, I can do a better job. But other things like acceleration, sometimes you cause more harm than good trying to do that. So.
Thanks. We have one more question from Shane. He asks, how do you see MBSE, or Model-Based Systems Engineering, being implemented moving forward? Do you think integration platforms like Model Center by Phoenix Integration will become the next big movement in the digital engineering future?
See, like I said, I've been doing this for over 50 years. When I was in school, there were no computers. I used a slide rule and even special slide rules. And I use computers, but I really, as Walt knows also, I'm really not really in the forefront of that area. And so maybe Walt would be better off to answer that question.
Well, model-based system engineering is the future. It's increasingly going to be model-centric and not document-centric. And that slide number 27 that Gene showed gets at the concept of model-based systems engineering, where you have everything feeding into a unified model that everybody speaks to. And we now are having the tools like InnoSlate is one tool. InnoSlate is a company that produces tools that can integrate all these models together. There's JAMA software, which does requirements integration. There's increasingly, it seems to me, but one of the things that I found out today that I was suspected, there's a thing called life cycle modeling language that purports to be headed in the direction of modeling the whole entire system throughout its life cycle. And that's been promulgated as a digital thread solution for this integration. So stay tuned. It's only going to get better over time. And eventually, what's happened in the past is that a lot of companies have come up with their own proprietary models, and like SysML and things like this that don't speak to each other. And so the focus now, the trend now is going to be to have models that integrate seamlessly and don't have to rely on proprietary standards, that basically put up firewalls between the different parts that you're trying to model. So
thank you, Walt. I also want to put a caution in about semi-empirical models, or even worse, empirical models. Is if you use those, be aware of the database. If you extrapolate outside of the database, the model will blow up on you and give you crazy answers. And you need to be aware from a physics point of view and engineering experience point of view of what are reasonable numbers, and in doing all. That's why when I had my design groups, I would typically pair an old senior engineer who may not be the best computer person with a young new hire who knew the models and whatever. And then, but you basically have to be able to have, balance those out so that you don't go overboard. Like I said, garbage in, garbage out, machine speed. The model is no better than the input data and the quality of the modeling that you put into it. And so just don't believe it. Don't believe it. If there's 8 figures that come out of that model, don't believe you have 8-figure accuracy. That's the danger sometimes of do a sanity check also with your model too.
Thanks. And Shane also mentioned that Georgia Tech has a great SysML course.
Yeah.
So that's good for people who are looking to learn more about it. There's plenty of resources online or at a lot of these schools. It's definitely the next big thing in engineering going into the future.
Well, UCF also has a SysML course that I'm teaching right now.
All right.
So the whole academic community is trying to get behind this impetus of
Good.
system modeling.
One of the problems we have is most professors are what I call an inch wide and a mile deep. They know a whole lot about very little, and so they often don't have system engineering experience. And there are a few schools like you mentioned, UCF and Georgia Tech and Auburn and UAH, Huntsville, and the military schools like Naval Postgraduate School and whatever. But that is one of the problems that engineers have is they go through the school and they get their analytical stuff pretty good. And they graduate and they go in industry and they have to be trained for a while in industry about the real world considerations that were part of their analytical environment at the university. But the schools that do that a little more, like Georgia Tech and others, I think that's worth a lot. You can get the young hire engineer on board and being productive at a shorter period of time.
Yeah, and two big bastions of this are Cornell University and University of Southern California are very adept at system engineering and degrees in that field.
Okay. Okay. Is that it? Got any more?
And I think that's all the questions we have for now.
Thank you all. Yes, very much.
Okay, well, we've gone over time and I'm going to turn it back to Chris. Thank you so much, Gene, for a very informative lecture.
Yeah, I guess you can figure out, I stopped sharing, right? That's what I should do. Here we go.
Yeah, go ahead and stop sharing. Okay, now
okay, got it. Got it. Okay.
There you go. So now we're back. And so, Chris, take it away.
Yeah, well, thank you, Gene, for coming to speak with us tonight.
Thank you.
It was a great presentation. I think everybody enjoyed it online. And thank you, everybody, for joining us. Had a great turnout tonight. Some great questions from everybody. Look forward to seeing you again, Gene.
Thank you. Bye now.
Yeah. Oh, Chris, quick question. Is it possible to see the attendance list that you might have from the YouTube or not? Are they anonymous or?
We can see people who've asked questions or commented, so I can send you that afterwards.
Just those people. Okay. That'd be nice to have that. Okay. Thank you. All right. Well, I'll sign off then, right?
Yes.
Okay. Bye, everybody. Thank you.
All right. Have a good evening, everybody. And you can always check out more information on our YouTube channel. If you're interested in any future events, we live stream most of them here. And we also have our website, engage.aiaa.org/Central Florida, as well as our Facebook page, which is just AIAA Central Florida Section. So be sure to check out future events. And if you have any questions or anything about us, you can comment anywhere there or find our email address, aiaa.central.fl@gmail.com. And you can find out more about Gene Fleeman. Pretty much just Google Gene Fleeman and you'll find him. He has a bunch of great books out there, published through AIAA as well, so they're on the AIAA website, aiaa.org. You can order the books through there, or I believe Amazon as well. Great textbooks, but also just great learning books. They're not quite as dense as a lot of the textbooks I've seen. So thank you, everybody, for joining us tonight, and have a great evening and a great weekend. And if you're in Florida, be sure to watch the 2 launches we have scheduled. We have I think a GPS or a spy satellite launch tomorrow, and then a crew launch, the first official crew mission for SpaceX on Saturday evening. For now, at least, hopefully the weather holds out. So thank you for joining us.